All right, kids, section 3.6. You guys got to be paying attention because this is one that causes trouble sometimes. I'm not going to do this opening problem. Answer is 165. You can check my solution document that'll be posted to Canvas as well. I'm going to focus on 2 and 3 right now here in the opener. So I hope this is intuitive. Take a look at this given here. It says that this entire segment here, this entire angle, BAE, is congruent to this entire angle, VWX. That also goes on to tell us that both of these big angles have been trisected. So the fact it's been trisected, of course, all three of these segments are congruent. All three of these angles are congruent to each other. All three of these angles are congruent to each other as well. But because the entire angles were congruent, that means all 6 of these parts are congruent, right? So we can actually set up an equation like that, and we're going to get x equals 5. So I'm finding the measure of angle BAC, but remember all 6 of these angles are the same. 15 plus 12 is 27. Now, of course, we have both of these being trisected and both of these big angles are congruent, which allows us to do that. Now, this next one's similar as well in that we're told that, but instead of being told that the holes are congruent, we're told that these 2 separate pieces are congruent. You see MO and NR. But then we're told that O bisects this whole thing and R bisects this whole thing. So I hope it follows then that if this piece is congruent to this piece, and these are both halves of these holes, and these halves are congruent, the holes would have to be congruent as well. So all 4 of these pieces would be congruent. So we do a little factoring here. This is going to be, whoops, I don't know where that 4 came from. We'll pretend that never happened. X minus 5, x plus 1. So you actually get 2 values for x. You get -1. You also get 5. And we have 2 answers here. If x is 5, this whole thing, that would be 25 times 2. You'd get 50. If x is -1, this still works. NR would be 1. The whole thing would be 2. We're all set. Okay, so this is multiplication or division. And this is on the back. Well, yeah. This is on your number 20 and 21 on the gold sheet, okay? I'm going to write it out here. If angles are congruent, then they're like multiples are congruent. And then it works the other way too. If angles are congruent, then they're like divisions are congruent. Now, this also works, both of them, with segments. So if you look at this, this first one that we did earlier, this is what we call the division property. You see, we were given that this whole angle was congruent to this whole angle. We were given that they're both trisected, and we were able to determine something of the smaller pieces. So that's like division. Here, this was multiplication property. We were given that these pieces were congruent. We were given that we had bisection twice, and we got the bigger, we were able to determine the bigger things. So, in order to use multiplication or division, you have to have a double. And what I mean is, well, here, multiplication property, let's be more formal. You use this when you know the pieces and you want to get larger, but must have a double. I'll explain what that means here in a second. This is when division properties, when you know the holes and you want to get smaller, you want to get the pieces. Must have a double. What I mean by a double is you have to, what multiplication and division does is it relates two totally separate things together. And the way we can do that is if we need to have both of those things need to be bisected, or they both need to be trisected, or they both need to have a midpoint, or they both need to be medians cutting the opposite side into two congruent parts. So if you don't have that that bisection happening twice, that trisection happening twice, that midpoint happening twice, it's impossible to use multiplication division. You have to have that double. Now, when you see that double bisection, double trisection, double midpoint, it doesn't guarantee that you're going to use multiplication or division. Okay, it doesn't guarantee it, but you could potentially. If you don't have it, it's not possible. Here, let's see if we can do an example, see if it makes more sense. So again, I'm going to start with step 2, like I usually do. Now watch this. JE is congruent to SE. ER is congruent to EI. Now here's our double. You see, R is the midpoint of this whole thing. I is the midpoint of this whole thing. We have to show that the wholes are congruent. So I'm thinking I might have to use multiplication. I have a double. I have to get the wholes. But you see, in order for me to use multiplication to get the wholes, I would first have to say that the halves are congruent. Now we're not quite there yet. Remember, this is congruent to this. This is congruent to that. These are the midpoints, R and I. So we could first say that JR is congruent to SI, right? And that would be what? If congruent segments are added to congruent segments, this is just what we were doing the other day, right? Then their sums are congruent. So now that this piece JR is, see, this half JR is congruent to this half SI, and we know that R and I are both midpoints, we can now conclude J is just a three-step proof due to multiplication. If segments congruent, then their like multiples are congruent. Now, a lot of times people would like to say that SI is congruent to IN because of the midpoint, and JR is congruent to RY because of the midpoint. And while that's true that JR is congruent to RY and SI is congruent to IN, it is not necessary to do this particular proof, okay? Once we have these pieces congruent, because there's both midpoints, we can just double it. So it's like a shortcut, okay? It's like a shortcut, a good legal shortcut. So here, let's take a look here. So the first thing I'm thinking of when I see this given information, I see this double. And that makes me think of multiplication or division potentially. So I have angle 1 congruent to angle 2. I have to get 3 congruent to 4. But look, you see, SC is bisecting this big angle. PR is bisecting this big angle. I have to get 3 congruent to 4. That's a piece. 3 is a piece of this whole thing. 4 is a piece of that whole thing. So if I could get these whole big angles congruent, then I could do division to get 3 congruent to 4. Now, can I get these whole angles congruent? Of course I can. Remember, angle 1 is sup to angle 3. Angle 2 is sup to angle 4, right? If the sum of two angles is a straight angle, then angles are supplementary. So now, if these are, if those are sup, oh, I made a mistake here. I got to fix this. Sorry. Sup 1's not sup to 3. Sorry about this. 1 is sup to angle ESN, right? And 2 is sup to angle NPO. My bad. But you see, remember, 1 and 2 are both congruent. That was given to us. So these two angles must be congruent because they're sup to congruent angles. So angle ESN is congruent to angle NPO if angles sup to congruent angles, then congruent. And you see, now we got these big angles congruent. So we can finish. We can say that angle 3 is congruent to angle 4. If angles congruent, then they're like divisions are congruent. All right. I'm hoping that wasn't too bad. This next one's a little bit longer. Okay, a little bit more going on here. So let's see here. KL bisects WD. So that means that's going to be congruent to that. And now I'm not going to show this bisection here because my diagram's just going to get too messy. I just got to remember, hey, I got this double bisection going on. I might have to use multiplication or division. Angle WNI is congruent to angle SEL. And you see how ES bisects DEL and IN bisects that. So I have the pieces, I could get the wholes. So, and then there's also says what? W, oh no, I already did that. So let me catch up to the tick marks first. Let me say that WR is congruent to RD if segment bisects a segment, then it divides it into two congruent segments. Okay, so we got that out of the way. Now, again, I kept a mental note of this bisection. Okay, so I don't have to say that this is congruent to this. I don't have to say that this is congruent to this. It's true, but what I want is I want this whole angle congruent to this whole angle. So we're going to say angle WNK is congruent to angle DEL. And that's what? If angles congruent, then like multiples congruent. Okay? And you see the whole purpose of getting that congruent to that is now I can get this angle in here congruent to that angle here. All right? Now I'm going to do it a little bit differently. Instead of doing the sup comp route, watch this. I'm going to say that angle KNR is congruent to angle REL. And that's because what? If angles are straight angles, then they are congruent. Now, if I say that that straight angle is congruent to that straight angle, and remember I said that this big angle is congruent to this one from like multiples, I can get this little angle, angle WNR, congruent to this little angle, RED, from subtraction. If congruent angles subtracted from congruent angles, then the differences are congruent. I want you to know you could have used the sup business. A couple of the steps would have been worded a little bit differently, but the sup business would have been the same number of steps. Okay. So we got this angle and this angle. We got this segment and this segment. Remember, I got those angles there. The vertical angles, angle WRN is congruent to angle DRE. And that's from vertical angles are congruent. And now we have triangle WNR congruent to triangle DER, and that's by angle, angle, side. All right. Down here, sorry that there's not much room here. The proof ends up not being too long. But, you know, I'm going to leave this for you. And then, you know, the solutions will be posted on Canvas on the solution document, as it usually is. I don't want to like give it away. I want you guys to try both of these, okay? This one is, of course, a proof because it says prove. This one is fine. You know, what is the measure? This is fine. You're going to use algebra for number 19. All right?